Hi guys, welcome back to the channel. In today's lecture, we are going to discuss about the plastic theory, or you can say that the plastic design method, right? So this plastic theory came after the working stress method, where in the working stress method, or you can say that which is also known as elastic method, we never allow our structures to reach the yield point. Okay, so what happened in the working stress method, if let us suppose this is the diagram of stress strain curve for mild steel. Okay, so this is the stress strain curve for the mild steel, right? So in working stress method, what we were doing is that, and let us suppose this is our yield point. Okay, this is sigma y and this is epsilon, which is strain. Okay, so in working stress method, what we were doing is that we never allow our structures to reach this sigma y value. Okay, so we apply some factor of safety to this value and limit our allowable stress to this point. Okay, so this is nothing but sigma y divided over my factor of safety. Okay, so what I meant by this term is that we never at any cross section, any fiber will have the maximum stress value. The maximum stress value on that fiber will be this value. Okay, sigma y divided by factor of safety. Anywhere in the beam or anywhere in the structure, that stress will not cross this value. Okay, so this working stress method is basically the elastic method. Okay, because we are in elastic range. Okay, this is the linear elastic behavior. Okay, so now you can see that we are underestimating the strength of the structure, or you can say that the strength of the member, because we can use this part also. Okay, this strength also we can use. Okay, we are limiting the allowable stress up to this point, but we are not using this strength, this strength of the material. Okay, so in the plastic analysis, what we do is generally we also use this the strength of this material in this range. Okay, this plastic range. What is happening in plastic range, as you can see that this is basically the plastic range. Okay, so in this this is basically, you can say that this is the ductility of the structure. This is also the ductility of the structure. What happens in the plastic design is that we are using the advantage of this ductility. The structure can absorb large deformation before any fracture take place. Okay, before any fracture take place, right? This is the fracture point. This is the fracture point, right? So in the plastic analysis, the deflection, what you can say that, as you can see that here, the strain is increasing. Okay, but stress is constant. Okay, so this is basically nothing but this is plastic flow. Plastic flow is basically what you can say that it is when there is increase in strain, but stress is constant. Okay, but structure is not collapsing, although the deflection in the structure will be more. Deflection will be more in structure. Why? Because we are allowing our structures to reach this point. We are allowing our member, any part of the we are allowing the member to reach to this point. Okay, so it is in the hand of the designer basically whether you want to design the structure by this working stress method, or you can design by this plastic flow method. Okay, all the structure, any structure will have some collapse load. Okay, means what I meant by that is that, if let us suppose if this is our fixed beam. Okay, so when you apply load on this fixed beam, when we apply load on this beam, let us suppose the maximum moment is coming at this point. Okay, so when this beam is failing, what we observe that we will have some yielding at this point. Under this point, some yielding will be there. Okay, and under this point there will be some yielding. Okay, so our structure is not failing at a single particular point. Okay, our structure will collapse. This beam will collapse when it will yield at this point. this point and this point. Okay. So basically, this is what you can say that the structure is not failing at a particular point. Okay. We will be having some collapse load to fail this structure. Okay. This is W collapse load to fail this structure. Okay. So basically in plastic flow, why it is called plastic analysis? Because we will be calculating the maximum load which structure can bear in this plastic range. Okay, in this plastic range we will be calculating what is the maximum load, what is the maximum collapse load which this structure can bear. Okay, and this working stress method won't help us in calculating the collapse load. Okay, because we are never reaching this state, we are always in elastic state. So in the working stress method we cannot calculate the collapse load of the building. Okay, right? So working stress method won't give us collapse load of the building. Okay, collapse load of the building. Okay, so if we want to calculate the collapse load, at what point the building will collapse, that thing we can calculate with the help of the plastic flow, right? And one more thing, when we are calculating the member section from the working stress method, we were restricting this allowable stress, okay, which is sigma y by factor of safety. So the sections which will be coming by designing of the working stress method are heavier section. Okay, so working stress method will give heavier section. Okay, but in the plastic analysis, you can see that we are calculating, we are also using this portion also. So it will give us some extra strength. Okay, so members will be cylinder. So in the plastic method, members will be cylinder. Okay, so when the members are cylinder, then in the serviceability criteria, that at the serviceable condition, the deflection will be more in plastic analysis design. The deflection will be more. Okay, because our sections are cylinder. Okay, because we have used the strength, because we have used the strength, because we are using this strength also. Okay, so that's why you can say that the deflection will be more. So if you want to design any structure with plastic analysis, we need to make sure that it should also fulfill the serviceable criteria. Okay, that it should not have excessive deflection in serviceable condition, right? So this is the basically the plastic, what you can say that this is basically the plastic flow. Okay, at this point, so we are using that concept and applying that concept in our concept in the design. Okay, now we need to idealize this stress strain curve. Okay, if we want to design through the plastic analysis, we need to have some we will idealize this stress strain curve. We have different model to predict this behavior, right? We'll be using the simplest method, in which, let us suppose this is sigma, this is strain. We will be assuming the elastic plastic behavior of material. Okay, so as you can see that in this thing we have idealized this thing like this, right? So up to this there will be Hooke's law. At this point, this is nothing but sigma y yield point, right? We are neglecting this upper yield point. Okay, that is not of much significance, right? And we are neglecting this strain hardening portion. This is basically the strain hardening portion, and this is the necking zone. Okay, so while you can say that while idealizing, we are neglecting this what you can strain hardening part. Okay, if we are neglecting this strain hardening part, it will be basically a conservative design. Okay, because we are neglecting the extra strength which will be provided by strain hardening. Okay, so remember that in plastic analysis, the true collapse load, the theoretical the theoretical collapse load will always be less than true collapse load, right? Why? Because we are neglecting this strain hardening portion. Okay, this strain hardening portion is neglected. Strain hardening is neglected. Okay, remember that thing, right? Why this theoretical load is less than collapse load? Because we are neglecting this strain hardening. Strain hardening is neglected. Okay, and that will be our conservative design. Okay, so now you can see that the behavior is, after yielding, the behavior is ductile. The behavior is ductile. Okay, so if we want to use the plastic analysis, the material should be ductile, right? The material should be ductile. Okay, so that's why the plastic analysis will be mostly applicable to steel structures. Steel structures. Okay, in RCC, the under reinforced sections behave like the under reinforced behavior will be ductile. Okay, so in RCC we will be having under reinforced structures, under reinforced structures. Okay, so this is the basically the idealized curve for the plastic analysis. Okay, and one more thing, this is basically the elastic plastic behavior. Elastic plastic behavior. Okay, this up to this portion is elastic, and beyond that this is plastic. Okay, but in ideal case, there is not a single material which will give us this behavior. Okay, this is the theoretical curve only, right? So now this is the basically on this basis we will do our analysis. Okay, after the crossing the yielding, we will be having this plastic flow. This plastic flow, right? So this is the little bit idea how the material respond in plastic analysis, right? Why we call it plastic analysis, we have already calculated, because the collapse load which we will be calculating will be in the plastic range. The material is in plastic range, and in plastic range we are calculating the collapse load for the building, right? This working stress method won't give you the collapse load. Okay, so in plastic analysis, we will get the true collapse load, means building will collapse after crossing that load, right? So now we'll study some behaviors. Okay, we'll study some behavior of a cross section when we will be study the behavior of the cross section when you can say that when we are applying load on that structure. Okay, so let us suppose this is our structure in which W load is acting. This is a beam. This is a continuous beam basically. This is the continuous beam. Okay, and this is basically indeterminate structure. Indeterminate. Okay, so what is over here is that if let us suppose the cross section of this beam is rectangular cross section. I'm assuming that this is a rectangular cross section. Okay, and these dimensions are B by D. Okay, so when we are applying W load on this, when we are applying this load on this, what you can say that on this beam, and let us suppose the critical moment comes under this point. Okay, this is the case of maximum moment. Okay, I'm assuming that the maximum moment is occurring under this point load. Okay, so now if I took the cross section of this beam. Okay, so what is happening is that let us suppose this is the beam. Okay, we took this cross section. With this, we took the cross section. We took the one section from at this point. Okay, and if you look the cross section, it will look like this. Okay, this is a little bit hollow, but it is not the case. Okay, this is the rectangular portion, basically B into D. Okay, so when the W load is applied on this beam, there will be some neutral axis. The upper portion, upper fiber will be in compression. Okay, so the compression will act like this from this side and from this side. Okay, so basically if you see this thing, the compression will be on top side and there will be some tensile force at the bottom. Okay, so at this fiber, at this portion, there will be some compression force, compressive force. Okay, and here there will be some tensile force, right? Okay, so now this is the front face of this beam. Okay, and this is the cross section of the beam, right? This is this face where the compression is acting on this cross section. Okay, one from this side, one force from this side, and here the tensile force is acting one from this side and one from this side, right? Now you can see that this portion is in compression and this portion is in tension. Okay, so this, as we know that the stress diagram correspond to this, will look like this. This is sigma. Okay, and this is also sigma, because this is symmetrical about neutral axis. So both the stresses will have, both the fibers will have same stress. Okay, this is nothing but this is tensile and this is compressive. Okay, one more thing, in the plastic analysis we are assumed that the curve of the stress strain curve will be similar for the compression and tensile behavior, right? The curve which we drawn earlier will be applicable to both compression and tension. But okay, so now, and what happened to the strain diagram? Strain diagram will look like this. Okay, there will be some strains, epsilon. Okay, so similarly, if this is the cross section, this upper fiber will be in compression. Okay, this will be in compression and this fiber will be in tension, right? This fiber will be in tension. Okay, so this, you can see that at this level, this cross section, this fiber will be in compression. Okay, here you can see that this is in compression, this will be in tension, right? So now, when this is the case, when W load is applied on this beam, now we increase what you can say that we increase this W load to W1. Okay, so what happened when W load is increased to W1? So we are assuming that when it is increased to W1, this upper fiber will be having some value which is called sigma y, and this is also yield at the same time, which is sigma y, because this is symmetrical and this is our neutral axis. Okay, so now what is happening, this is our cross section. Okay, so this top fiber is yielded. Okay, at the stress at this point is basically sigma y, so this top fiber has yielded. Okay, similarly this also yielded. Okay, now what will happen to the strain diagram? The strain diagram will look like this. This is epsilon y and this is epsilon y. Okay, the strain will be to correspond to this stress limit. Okay, so we have seen this diagram. Okay, we have idealized this thing. So this is our epsilon y and this is our sigma y. Okay, so this is the case when W is increased to W1, right? Now let us suppose this load value is the W1 is increased to becomes W2. Okay, we are increasing the load. Now what will happen? Okay, as you can see that from this graph, this curve, the strain value, the stress value will be constant. Okay, so if we draw the stress diagram, and again, if this is a cross section, so this upper fiber after application of this compressive force is yielded. Okay, it is yielded. Okay, so the stress will be sigma y. Okay, so this stress will be sigma y, this top fiber, and this sigma y will continue up, will be constant for some of the fibers below this top fiber. Okay, and after that we will be having some linear behavior of this stress. Okay, so this portion, the fibers from the some fibers from the top are yielded. Okay, are yielded. Okay, so this is basically the yield stress. Okay, so this portion is yielded. Okay, and at this point the stress is sigma y. Similarly here, this is sigma y. Okay, so this is the case when W1 is increased to W2. Okay, now what will be the strain diagram? Strain diagram will again look like this. This fiber epsilon is exceeded epsilon y. Okay, similarly the strain diagram will be, it is a linear behavior, because we have one assumption that the plane section remain plane after bending. Okay, so for that the strain should be linear, the strain distribution should be linear. Okay, so this here also the epsilon should be greater than epsilon y. Okay, strain will increase. Okay, after yielding this section sigma y, this fiber has reached the yield point sigma y, but its strain will increase. As you can see from this curve. Okay, strain will increase, but the stress will remain constant, right? So again, when we increase W1, W2 to W3, now what is happening? What will happen? Okay, the entire structure, the section before the neutral axis, this is neutral axis, will yield. Okay, the yielding will start from the top fiber to this neutral, from the top fiber to this neutral axis. The yielding will start from the top fiber and it will come down to the neutral axis. Okay, so here the stress is sigma y, and here also the stress is sigma y. Similarly here sigma y, at this point this is sigma y. Okay, so you can see that at this point all the fibers in the structure has yielded. Okay, all the fibers in this structure has yielded, right? And the strain diagram correspond to this will look like this. This is, let us suppose this is epsilon 2. This epsilon 3 will be greater than epsilon 2. Similarly here, epsilon 3 is greater than epsilon 2. The strain will increase. The strain diagram will always increase. Okay, this strain is less than this strain. Okay, so strain diagram will be always increasing. Okay, so this is the case. So when we reach this points, this section cannot take any more moment. Okay, so this is the ultimate capacity at this point. So this is the ultimate capacity at this point, and we know this, and we call it as plastic moment, MP, which is also called the plastic moment. Okay, this section cannot have moment more than this plastic moment. Okay, right? So that's why the concept of the plastic moment came, because we are saying here that we are in the plastic range basically. So through that we are calculating this plastic moment. Okay, now you can see that what is now from this discussion we learned that how the material behaves from the elastic range to plastic range. Okay, so this behavior we have studied. This is nothing but this is elastic behavior. Okay, when it is yielded, this is basically a yielding has started. Okay, yielding has started. Okay, and the moment which we got from this curve is nothing but yield moment. Okay, now after that thing, this is basically the elastic plastic behavior. Why? Some of the fibers are in elastic state and some of the fiber reached plastic state. Okay, this is plastic and this is elastic. Okay, some of the fibers are in elastic state, these upper fibers are in plastic state, and these fibers will be in elastic state, right? And after crossing this state, we are reaching, this is the plastic state basically, plastic state, where the whole complete fibers are reached the point which is called sigma y. This is a complete plastic state. Okay, and the moment correspond to this plastic state is plastic moment, right? So this is the way your structures behave in the plastic analysis. Okay, so so this is in this way basically the discussion is to tell how the material behaves in this plastic analysis. Okay, now by using this concept, we will be calculating what will be the plastic moment for the sections. Okay, what will the plastic moment for the sections, and we will design our beam according to that plastic, according to that moment. Okay, so guys, if you have any doubt regarding this, you can write in the comment section. Okay guys, so thank you very much.